Hello James, today you can believe you can or you cannot, and you'll be right, because if you believe you can, you'll find a reason to, or if you believe you can't, you'll find a reason not to. The choice is yours. Today I invite you to join me in question bank number 6, wherein we'll be getting 10 questions stronger in the chapter of rotational motion. This is the grind for BITSAT 2025, wherein with every chapter of this series, we are discussing 10 questions and getting ourselves closer, 10 steps closer to our goal of getting into bits. Okay, so with that being said, I invite you to take on this challenge, be stronger than your strongest SQs, and let's battle out the questions. As the fans of this series will know, firstly we discussed the previous year question weightage across the different topics in this chapter so that we know which is the most favorite topic of BITSAT and we can concentrate our forces over there, and of course not neglecting the other topics, as BITSAT is a different game. Diverse questions can be framed from different topics. Okay, so let's begin with that. Let's see the previous year weightage. So from center of mass we have 5 questions being asked from the era of 2013 to recent. Okay, so then we have questions from torque and rotational motion in general being asked, 5 questions from there. Then questions also on rotational equilibrium, so we'll have to balance out the torque, then angular momentum and the angular acceleration. So equations of motion in rotational motion you can have. So 3 questions from there. Then we have rolling, pure rolling, or maybe sliding, slipping, rotational, rotational motion, rolling down an incline, one of the favorite topics of BITSAT. So from there 5 questions were being raised. Then we have moment of inertia, most favorite topic of BITSAT. Every year there will be one question from moment of inertia in the paper that you are answering. I called it out, so do what you will do of that. Okay, so here from there we have about 10 questions being raised from moment of inertia. Okay, we'll be practicing a lot of that too. Then we have questions on toppling, just 2 questions from there in BITSAT. Okay, so that was the previous year question weightage. So let's begin with the questions. Come to question 1 and 2 over here to kick things off. So in question 1 we have a wheel with angular acceleration this, angular speed this, and we have been doing it for 2 seconds. Okay, we are doing the rotations for 2 seconds. You are supposed to tell what is the angle it will rotate by. Okay, so you can use this equation which we use in uniform accelerated motion, s is equal to ut plus half at square in the angular analog. Okay, so displacement, angular displacement, velocity, angular velocity, time is time, of course, acceleration, angular acceleration, and t square. Okay, so just substitute the values. Omega is 2, right? Angular speed is 2, time is 2 seconds plus half, alpha is 3, time is 2 seconds, and that's squared. Okay, so this and this cancels, 2 2s are 4 plus 3 2s are 6, right? So 10 radians. It would have been rotated by 10 angles in time of 2 seconds. Okay, so that is your answer. Pretty straightforward. Just take the angular analog of this equation, right, to find the angular displacement. Now let's come to this one. Here we have 4 rods, each of mass m and length l. They form a square as shown. The moment of inertia about any side of the square. Okay, so it's passing through one of the rod, so that rod will not contribute to the moment of inertia, right, because it is on the axis. Okay, so there is no effort in rotating that rod. Okay, so this rod basically will not contribute. And for here you are supposed to know for a 1D rod the moment of inertia, right? Even in NCERT you learn about these 2 axes. Okay, you learn the moment of inertia about the edge, and about the center of the 1D rod, right? So this is mass m, length l, right? So you'll know the formulas. Here it is ml square by 2l and ml square by 3. If you have difficulty in remembering this, just picture which one will be difficult to rotate. Okay, about this axis is it difficult to rotate, or about this axis is it difficult to rotate? You can see, right, the difficulty is in rotating about the axis at the edge, since the mass will be distributed very far from it. Okay, so this will have higher moment of inertia. That is what I'm saying, right? It is a moment of inertia is the analog of inertia in linear motion, right? So here there is more difficulty in rotating, right, than here. So here the angular moment of inertia at the edge is greater. Okay, so here it will be higher. So if you know and if you confuse between these two, that is a trick to remember. So if you see these 2 rods 1 and 2, they are at the edge, right? This is the configuration for them. The basically the axis that we are considering over here is at the edge of these two rods. So here it will be 2 ml square by 3. So ml square by 3, ml square by 3. Okay. Now this rod. What about that rod? Okay. No need to use such theorems and all. We can actually just treat this rod as a discrete mass, since this is the axis. We have considered this moment of inertia. Now we can consider this as entire mass is concentrated on the center of mass m, and here we'll have yes, and its distance, perpendicular distance, right? So that's why that length is not very significant. Okay, perpendicular distance from the axis is L. So basically mass m at a distance L from the axis, so ml square. So that is your moment of inertia. 3 plus 2, 5 ml square by 3, which is, this should have been small m, right? We're taking the mass as small m. Anyways, just a notation. And option A is the correct choice over here. Over to the next question. 3 and 4 over here. In question 3, we are asked about a drum that is rolling down an inclined plane. Okay, it's rolling down without slipping. What does the frictional force do? Those who know the concept will know the role of friction. What does friction do? It induces rolling rather, right? So if you see, if there was no rolling, okay, so if there was no friction, okay, if there was no friction, if this plane was smooth, what will happen? Okay, this block, this drum would not have any um, angular motion. Why? Because the velocity will be in this direction from the center of mass, right? And it will just, the drum, you can picture this, since there is no friction, will slide down. Okay, it will slide down, it will not roll. Since there is friction, there is torque about this. Okay, and that causes rotational motion. Okay, so, and since there is friction, it will reduce the translational motion, right? So in the direction, since the block is sliding, suppose you have a block, the block is sliding down the inclined plane and there is friction, it is opposing the motion, right? It is opposing the tendency of motion. So if the block wants to move down, friction will oppose it. Okay, so it's kind of reducing your translation motion. But here in the case of drum, since it is reducing your translation motion, of course that is happening, but it is also providing a torque, R cross F, right? So it is reducing your rotational motion. So converts translational energy to rotational one is the correct choice. Okay, others are just opposite of that. If you see, that can't happen, right? It does not promote translational motion, rather it opposes it, friction. So dissipated as heat, then decreases rotation, it increases. Okay, it converts translation to rotational energy. Okay, so let's come to this one. Here we have a circular ring, I believe. Okay, this should be a ring of mass capital M and radius R. Okay, so here we are adding 4 masses M, okay, on the perpendicular ends, right? 4 object of masses M are gently, so held gently, that is a key word over here, gently, at opposite ends of the rings. Of course it's a ring, so 2 perpendicular diameters, so M. Okay, so you have a ring and not a disc, a ring, right? And then MM, okay, 2 opposite ends and they are perpendicular in the plane, you can see. So we have MM. What are we supposed to tell? If we add this gently, what will happen to the angular speed? So initially the ring was rotating with omega. Now you add this pieces gently. What will happen to the angular velocity? Right? So you can picture it. Initially it is omega. Now you are putting some more masses, so it will slightly reduce. Right? So you can make logic here. If you see m plus 4 omega upon m, right? This is greater than omega. Okay, so this can't be the correct option. By logic, it should reduce, right? And here we can't make out. This is less than omega, right? Yeah, this is less than omega. M minus something, m plus something. So less than omega. Now this capital M. Now this depends. Okay, we'll find out. So we'll use I1 omega 1. So gently is the keyword over here, because this means that there is no external torque while we do this. Okay, so I1 omega 1 is equal to I2 omega 2. Some of you might have directly used it, because how the hell else do you solve this question? Okay, so initially momentum of the ring, what is the moment of inertia of the ring. I is m r square, right? M r square. Mass m, capital M, radius r. Initial velocity, we'll take it as omega. Then I2 now we have the ring plus we have this 4 masses at a distance r, 4 discrete masses, right? So m plus also this 4 masses, 4m, and all are at a distance of r square. Now this omega 2 we have to find out. So omega 2, simply you can see that it is r square, you can cancel anyways. So m upon m plus 4 capital M plus 4m into omega. Okay, of course it is less than omega, you have added masses. Okay, the cancel of this. So here anyways this is the correct choice. Just calculate it using conservation of your angular momentum. I1 omega 1 is equal to I2 omega 2. So that's about this question. Over to the next one. Question 5 over here, we are supposed to tell what is the torque about this point A, okay, and the forces are as shown. Okay, so we have to find the resultant torque due to all these forces. Okay, keep in mind also the direction of the torque. Okay, not all will add up. Some will be in the outward direction, some will be in the inward direction. Okay, we'll determine that using the right hand rule, right, right hand thumb rule. So first of all, you can see this 90 newtons is at the point A, right? If you want to find torque about A, okay, so if you push the door at the hinge, there won't be any torque, right? If you want to rotate the door, you push at the handle, not at the hinge, right? It won't move the door. So this force will not result in any torque because torque is R cross F, right? So if R is 0, that will not produce any torque. Okay, so we'll be using R cross F across the different points and we'll find out the torque. Okay, so let us find torque at point A due to this. Okay, due to these two forces. So let's write tau 1. Okay, so tau 1, tau 2, tau 3, tau 4. Okay, so now so I'll also write this as RF sine theta. Okay, the magnitude basically. Okay, or you can also add the vector. Okay, vector will adjust that inside, either it will be outward or inward. Okay, so tau 1 is this one. Okay, so here if you see R is like this, right, R cross F, right, and how do you measure the angle between any two vectors? Either you match their heads or match their tails. Okay, this if you see this is the angle between R cross F, you are completely wrong. Okay, so you have to match their tails or match their heads. So you have to match, so you have to move this vector like this. Okay, so the angle between them will be 30, not 120. Okay, you match their tails or match their heads, or you can also do that, you'll get 30. So tau 1 will be L by 2, which is 3 by 2 R cross F. Okay, F is 80 and sine theta, right? So if you see the angle between them, I told you it's 30, and in going from, so we bring R over here, right, to match their tails. So R cross F is in the outward direction. So outward direction will denoted by positive. Okay, so R cross F and sine of 30, which is half again. So this and this cancels. This becomes 40, 4, so 20, right? 4 2s are 8, 4 zeros are, so 3 2s are 6, right? So plus 60. So this is producing a torque of plus 60 Newton meter. Okay, this force. Now torque due to the second force at this point, this force over here, you can see that this will make 90 degrees, right? So this is vertically down. So sine 90 is 1. So you just have to do R cross F. Okay, R, and we have F. Okay, again you have to match the tail. So you bring R over here. Okay, R over here, and F is like this. Okay, so R cross F, R cross F. Okay, now it's in the downward direction. So this torque is moving the rod like this. This torque about A is moving the rod like this, right? It's opposite. The two torques are opposite. You can see that. So R, again 3 by 2 cross F, which is F is 60 and sine is 90 degrees, sine 90 is 1. So here we have 2 hamaza, 2 threes are. So 3 threes are minus 90. Okay. So now tau 3. Okay. Was there an option for the directions? Okay, let me check that, because since the directions are not mentioned in the question, no, the directions are not as such mentioned. So conventionally they are treating plus as outward, minus as inward. Okay, that is what we'll go by for the time being. So tau 3. Okay, let's calculate torque due to this one now. Again, so we have to match the tails, right? Match the tails of the vector. So here we have 70 newtons, and this r will be, r now will be from A to this point, right? So this whole vector, okay, from here point A, right? You are finding torque about point A, so r is from here to here, okay, and you move it so that you can match the tail. So this is 60 and 90, so that is 150. Okay, so now r cross f, you do that. So 70, and for wait, let's do this first. So r is 3. Now it's the complete length, cross f 70, and what is the angle between them? Sine of 150. Okay, we'll discuss the direction based on r cross f. R cross f, outward direction, so it has to be positive. Okay, r cross f, r cross f. Okay, outward. So we have 3 into 70, and sine 150 you can write as sine 90 plus 60, right? 90 plus 60. So this you can write as sine 90 plus theta will be cos theta, right? Cos 60, sine 30 half, cos 60 half. So this is half, this is 35, and 30 30 90, and plus 15 105. So 105 Newton meter due to this. Okay, yes, positive is taken as outward and negative is inward. Okay, I'll tell you by the answer. Then we also have this force of 15 newtons, but the problem with this force is that it is pulling the door like this. So if you, the door is like this, it opens like this, suppose. Okay, you stand parallel to the door and try to pull it like this. Okay, so it won't cause rotation, right? That is the case over here. Or if you want to see r f sine theta, sine is r and f are in the same direction, sine 0 0. Okay, math won't lie. So here what is the net torque now? Torque net, you just have to add the 3 torques with their sign, since we have considered the directions in their signs. So 60 plus 105 minus 90. Okay, so this will give you something wrong. This will give you, no, it's correct, minus 30, and if you remove 30 from 100, it's 70, so 75, right? So 75 Newton meter. So option D. Okay, so they have considered plus as the outward, although it's not mentioned. Okay, but that is the convention, general convention in the NCERT too. Plus is outward, minus is inward. Okay, so that's about this question. Over to the next one. Question 6 and 7. In question 6, we have 5 uniform discs of diameter d and mass m each. Okay, they are laid out as shown. So this is the x-axis, y-axis. You are supposed to tell what is the coordinate, y coordinate of the center of mass of the system. Okay, so let's only focus on the y coordinate. So if you see, this one will have, this is origin, right? X and y are meeting. So here the y component is 0 basically. So this one will not contribute. Even if you see this one, it has y coordinate 0, right? So we want y c o m, right? So it will be m1 y1 plus m2 y2, so on up till m5, right? We have 5 disk, 1 2 3 4 5, right? And all the sums. Okay, so that will be basically 5n, because each one has equal mass. But if you see m1 m2, okay, they are at their y coordinate is 0, so basically they will not contribute to the y coordinate of center of mass. Okay, whereas in this cases we'll have some contribution. So let us write y c o m. So here m is common anyways, so y1 is 0, I'm saying, y2 is also 0. So this one, you can see the y coordinate, it is d, right? R plus r, right? The diameter is d, so r plus r, 2r is d. So here we'll have 2d, m at a distance, m mass m at a distance of 2d. Okay, then we'll have this one. This one, if you see what is the y coordinate, it's d and d, right? So it's d in x, r plus r, d in x, and r plus r to d, which is in y. Okay, so it is d and d in x and y, so we only considering the y coordinate, so it is d. Okay, so here it is also d, not 2d, r plus r, 2r, which is d. So let's come to the last disk, which is at a distance of d plus d, right? D plus d. So r, 4r or 2d. Okay, and in the denominator we'll have m. Okay, total mass. Okay, this is not contributing, meaning mass is not there. Of course, it's there, right? m1 plus m2 plus m3. So we have to rotate the total system. So here it will be 5n. Okay, so this and this will cancel. So 2 plus 2, 4, right? So 4d by 5, which is option B. That is correct. Okay, you just have to consider the y coordinate, use this formula, and cleverly see, okay, at what position is the center of mass of each disk located. Okay, so that gives you your answer. Let's come to this one. Here we are supposed to find the moment of inertia about this axis COA. Now we have three masses m, equal masses at the vertices of an equilateral triangle, so all these sides are equal. Then you are supposed to tell what will be the moment of inertia about this axis COA. Okay, and this axis is passing through this mass m at O, and of course it is in the plane. Okay, it's not like this or going in. Okay, it's in the plane, okay, of the figure. So your figure is in the plane of the board, and we have an axis like this. So the axis is like this. Okay, it's not coming out or going in. So that is key to know. Okay, so here if you see, this mass is on the axis, sitting on the axis, right? So its moment of inertia contribution will be 0, and here this mass is at a distance of m, so I can write as ma square, right? Mass into distance square. Okay, now again this mass we have plus something, right? So you can eliminate certain options. This is less than 1, right? This is less than ma square, 0.6 ma square it will give you. So of course we'll have something more than ma square. Okay, so let's calculate now. So here if you see, this mass is at a distance of, now you are not supposed to take this distance and mark 2 ma square, because when you calculate moment of inertia, you measure distances from the you measure perpendicular distance, right, from the mass. Okay, so here this is the distance perpendicular to the axis. Okay, there is the mass located, so this distance we are supposed to find. It's easy, we can find it via geometry. So if I drop an altitude or a perpendicular, it will cut it in equal halves, because it is an equilateral triangle, and the altitude will basically be the median. Okay, that is also true for isosceles triangle. So here we will have a by 2, so this will be also a by 2. Okay, I hope the logic is clear, or you can use trigonometry in this case also. So yeah, this will be 60, this will be 30, you can use, right, all angles are 60, so you can use trigonometry in this triangle. This is 90, and yeah, you can do all of that, right? Sine 30 basically, half, right? Sine 30 half. Okay, that also we did. So here what is the mass? M, at a distance a by 2, so a by 2 the whole square. Okay, so I will be ma square plus ma square by 4. 2 square is 4, right? So 4 plus 1, which is 5, so 5 ma square by 4. Okay, where is that? Option C. Okay, so that is your correct answer. Over to the next one. Come to question 8 and 9. So in question 8 we have 4 masses joined to a light circular frame. So this is not a ring, it's just a circular frame, and it's light, basically negligible mass. So the radius of gyration of the system about an axis, that is, so this is your circular frame with the masses at the perpendicular opposite ends. So you are supposed to tell what is the radius of gyration. Okay, if you go for the definition, you'll confuse yourself, but we'll calculate it simply by a simple concept. Okay, you'll get to know about it. So this is the plane of the circular frame, and we have this axis which is perpendicular and passing through the center of the circular frame. Okay, now first of all, let us find moment of inertia. Okay, now these are discrete masses, each at a distance of r, right? R, right? So you just have to multiply this with r square, 3m plus 2m plus m plus 2m into r square. Each of this is multiplied by r square, distance from the axis, right? So 2 to 4 and 3 7 8, right? 8 mr square. Now to find radius of gyration, basically you write I as mass total into k square. Okay, now this k square you'll get when you equate this two, you'll get a relationship between k and r. Okay, so that will give you the relation over here. Here the radius is a, so I'll write it a. Okay, so you just compare this two. Mass total is again 8m, and we have k square, and here 8m a square, right? So this implies that k should be, since it's a radius, let's take the positive value, k should be equal to a. Radius of gyration should be equal to a. Okay, this was a simple question. We only had discrete masses, but you can try to find the radius of gyrations for different systems, right? You have like a solid sphere, or you can have hollow sphere. In each of those cases, you can try to find out the radius of radius of gyration. Okay, just equate the moment of inertia that you get. You'll know the moment of inertia of this different system, right? A rod, and then we have spheres, hollow and solid, cone, hollow and solid. So you can equate it to mk square and find it in that term. So that will give you the radius of gyrations. Okay. So here let's come to this question. We have a uniform sphere which is rolling down an inclined plane. This inclined plane has an angle of 45 degrees. Slipping down, sorry, it's rolling down without slipping. So yeah, then we are supposed to find what is the value of this mu. Okay, of course there should be friction for rolling. So what is the value, minimum value of mu? Okay, so friction basically you can write it as mass into acceleration, right? And acceleration, no, we won't do it this way. Okay, friction is, in case of rolling, if you find out, it is mg sine theta by 1 plus mr square by I. Okay, and if you want to find the acceleration, this is like one of the favorite questions. This is unrelated, but I'm just mentioning it over here so that you know it. Sometimes they might throw down or roll down your two different kind of material, like a hollow sphere and a solid sphere. They might ask you to find the ratio of their accelerations down the inclined plane. Okay, so you can find it out using this formula. Okay, and it will only depend on this I, right? When you for different systems, the I will change, and that will lead to different acceleration. So different things roll down at a different rate down the inclined plane. So that is the concept over here. Okay, and acceleration and mass are like inverse related, so kind of in this case. So we have that uh, opposition, you can say, the inverse ratio. Okay, in case of the friction force over here. Okay, not the exact logic, just a crude way of remembering it. Okay, so you just switch this. Okay, inverse. Then what will be the friction? Friction is given as mu n, right? And n in the case of inclined plane, it is mg cos theta, right? Because you have along the incline mg sin theta, and perpendicular to the incline mg cos theta, right? So this mg cos theta will give you the normal force. So mu n, and n is mg cos theta. So that is the logic. Okay, so you don't need the mass in this question, and they have not given it. Mr square by I. We should know the moment of inertia. For a solid sphere, it is 2 by 5, right? 2 by 5 mr square. Okay, for a hollow one with the same mass, so hollow one will have the same mass, but at the edges, right? So it will be slightly higher, so 2 by 3. So that way you can remember. So mr square cancels, mg also cancels, so you are supposed to find mu. Okay, so mu will be, we can take this cos to the other side. Sin by cos is tan theta, so tan theta upon 1 plus 2 by 5, or 5 by 2, right? Mr square upon 2 by 5 in the denominator, so 5 by 2 we can write. So this will give us tan theta is 1, right? Because theta is 45 degree, tan 45 is 1, and in the denominator we'll have 7 and 2. So 7 by 2 will have, so that we can take that in top. So 2 by 7, okay, 28%. So 2 by 7 is the correct choice over here, and that is the concept how you do it. Okay, that is the acceleration key tip formula. Some appeared in the previous BITSAT questions. So yeah, that also you can remember. Just inverse over here. Okay, for friction, and mg, of course, it's a force, right? So that's about these two questions. Over to the last question for the day. Question 10 over here. In this, we have pure rolling down the inclined plane as shown. Okay, so here we are supposed to find the velocities of point, the ratio basically of velocities at point B, C and D. Okay, C is the topmost point, B is the center, A is the point of contact, and D is the point just opposite to D, B, sorry, okay, on the sphere. So here it would have been 1:1:1 if there was no pure rolling, there was no rolling. Okay, since the block would have, or the ball would have moved as a rigid body down the incline, so in that case it would have been 1:1:1. All the points would have had equal velocities as in the case of rigid body. But what is happening over here? Rolling, right? So each point will have a different velocity. For instance, what will be the velocity of point A? If you know the concept of pure rolling, right, here it will be 0, right? So if it's 0, this is a question for you to ponder. So if it's 0 at this point, why is it moving? Okay, why is this point getting moved? Okay, why is this block is moving? Okay, or is it really moving, or what is happening to this point? Okay, if this is 0, how it is moving? Okay, that is something that you'd answer me in the comment section. Okay, I know the question is a bit ambiguous. Okay, I'm not able to frame it exactly, but yeah, if this is 0, tell me the mechanics. How is it working? How is this block rolling down still? Okay, or what is happening to this point specifically? Okay, how this point over here will come to this point. Okay, if the velocity at this point is 0, how is this point reaching this point? That is the question. Okay, so then so this being taken for granted, since we know that the contact point at the point of contact in pure rolling will have velocity as 0, we can find all the other velocity from this. So if you want to find VA, so if you want to find VB, okay, VB minus V, right, concept of relative velocity, then if you want to find VB, we can have VBA minus VA. So in all the cases we can write the velocities at point C. If you want to write, it will be VCA plus VA, or VD is VDA plus VA, and we know that VA is 0, right? So we can directly write this velocities as relative to this point. Okay, so VB is VBA. So how will we find that? VBA will be the distance from the point A, which is R, and the angular velocity omega. Okay, it will be in the pure roll, right? So this is the velocity at point B. Now how do we find the velocity at point C? Okay, now again the distance over here, it is the topmost point, so R plus R, 2R, right, and into omega. So distance from the point A into omega, that is what we are doing. So this is how you find those. So VD, now this the distance from the point A, okay, not point B, point A, right, we want VDA. So what will be that? So if I draw a zoomed version of that, so this is point B, this is point D, right? So this is R, also this is R. Okay, so what will be this? Okay, it's actually like this. Okay, this is 90 degrees. Okay, this will form a quarter, right? So this and this, if you see, B is over here, D is directly opposite, so it will form 90 degrees basically. So this is R, this is R. What will be this? R root 2, right? It's like square, the diagonal is root 2 times the side, right? Or you can use Pythagoras theorem. So R root 2 it will give you. So the distance from the point A to point D is root 2 R, we can say, and again the velocity is omega, right, for pure root. So we'll find VB is to VC is to VD. So that will give us VB is R omega. So R omega is common throughout. So 1 here VC, right, VC we want, so 2, okay, and VD is root 2. Basically they are proportional to the distances from the point A. if you can note that. So the correct option is option B. Okay, so that's about this question. I hope you really enjoyed this session. To answer about VA being 0 in the comment section below, and I'll see you soon in the next video. It's Christmas Eve today, and if you celebrate Christmas, Merry Christmas and a Happy New Year. I'll see you soon in the next video. Till then, keep working hard, keep enjoying physics.